Hi everyone, my name is Miraj Jolai, and I'm a prototyping architect on the Asian prototyping team here at Amazon Web Services. I'm glad to have you joining us today for the AWS Summit Online. In this session, I will talk about MLOps by using a real prototype that we have done for a customer as an example to show how to automate and create pipeline that will help you to train and deploy ML models automatically. Let me start by introducing you the prototyping program. If you already gone through some of the session on this track, you might be already familiar with what I'm going to say. In case it's the first session for you, then maybe this will help you to understand a bit more about what the prototyping team does. The AWS prototyping program helps to contextualize complex uses of the AWS platform by building working prototypes of specific customer use cases, leveraging existing data, devices, and systems. The prototypes we build are not production-ready solutions, but rather enablement tools that demonstrate the art of the possible and help customers to evaluate the use of AWS services. They are usually constrained in scope and time. We deliver them in a time frame that varies from 4 to 6 weeks, after which the customer can use what we have built and extend it in order to move to a pilot or a full production solution. In every prototyping engagement, we usually start from what the customer needs and work backwards from there to identify the right technology and solution that will help the customer to solve their problem. In this specific case, the customer operates in the manufacturing industry, producing pen, pencil, and other office supplies. Oftentimes, in an industrial environment, the quality assurance process is error-prone, done manually, and rather inefficient. With this prototype, we help the customer to address some of their main pain points. They approach us with a specific problem: how to identify defective items in a production line by using computer vision and deploy the same mechanism across all the other lines in the factory. This specific prototype needed to help the customer to automatically detect defective items in the production line, improve the output quality, and reduce redundant manual operations. But more importantly, the solution will need to be deployed easily across all the production lines. To put that into perspective, you can assume that the items produced during the manufacturing process are moving in a conveyor belt. In one of the stations of the line, we place a camera that will record the items from the top and verify in real time which of the items in the specific frame is defective. Each frame captured by the camera might contain multiple items. The ultimate goal is to reduce to zero the defects and generate an output that will only have items with expected quality, while allowing the customer to deploy this solution across other production lines where items might also be different. For example, some line might have pen, other line might have erasers. As I was saying earlier, prototyping is constrained in time and scope. As such, it's crucial to focus on the right task and avoid derailing from what will help to solve the problem. In each engagement, we focus on what brings the main value to the customer and reduce friction by leaving optional tasks at the end, if time is left. In this specific use case, we started the prototype by focusing on the machine learning problem, and thus the required activity to make them working as expected. Data, architecture, and core ML implementation were the main focus when we started this engagement. One of the crucial aspects on each machine learning workload is data, and in our case, that was not different. From the beginning, we wanted to make sure that the data used to train the model was enough and of good quality. Understand whether we will need to pre-process the data or extend the dataset by using augmentation techniques, and eventually find out who will own the labeling part. As the specific problem was around computer vision, data collection has been performed by considering the real-life environment where the solution will be deployed, and the resulting dataset was used for the training. After we got our data part settled, it was time to understand how to design the target architecture that will help to solve the core machine learning problem. Ideally, we will want to visualize and picture how it will run to understand whether we need to do some extra improvement during the training phase, if we have to pay extra attention to performance, or identify any pain point to be tackled in advance. Special attention has been paid to the algorithm to use to solve the problem, data to collect from the edge devices, and the action to perform in case of defective items have been identified. As I was mentioning earlier, the inference will run at the edge, and the camera that detects the item in the production line will be placed in order to take picture from the top and capture what is running under the conveyor belt. In each frame, the camera will capture a certain number of items, for example 5, and each of these items need to be classified individually in order to detect defects. In the target architecture, we accounted that, and this is why we have 2 models that will be needed in order to solve the problem. One model will recognize the item in each frame, for example pen, while the other model will detect if the individual pen is defective or not. Breaking down further the problem, we focus on what was required in order to recognize the relevant items in each frame. To solve that, we will need an object detection algorithm that is capable of identifying the items. The built-in SageMaker single-shot detector was ideal for this use case. As it is a supervised algorithm, we'd need to provide label data as input to train the model. As a result, after we acquire the relevant data, we will need to run through a labeling job, where users will be drawing bounding boxes around the items that we are trying to detect. Once the dataset is labeled accordingly, we can split that into training and validation, and eventually train the model with the resulting labeled data. After we know what are the relevant items in the image, we have to understand what can we do in order to identify the defects. We decided to use the built-in SageMaker image classification model for this task, which is also a supervised algorithm. The input of this model is no longer the full image, but the individual item that have been cropped from the full picture. That is why we added a pre-processing part that will use the previous labeling annotation performed for the object detection to crop the individual items from each image. The individual items will then be used as an input dataset for the labeling job. And eventually, the labeled image are split into training and validation, and given as an input for the image classification training. The labeling job, in this case, will ask the user to decide whether the individual item is defective or not, instead of drawing bounding boxes. Now that we have consolidated the architecture and prepared our data accordingly, it's time to work on the core ML capabilities. Amazon SageMaker offers great tools that allow you to work on your problem without requiring additional infrastructure configuration. With Amazon SageMaker notebook instances, you can launch your Jupyter notebook on demand, use it to document your ML process, and write the logic needed to solve the problem. You can do experiments and verify whether the approach identified at the beginning is correct, select or change the algorithm for the specific problem, or understand if you need a data preparation phase, where will you be required to run augmentation techniques to extend your dataset, or any other transformation task. You can iterate in your solution and change the hyperparameters on demand in order to get the best results. You can decide the number of epochs for the training, number of layers of the network, the optimizer to use, and so on. You can even launch a hyperparameter tuning job to help you identify the best hyperparameter values that result in a model that performs the best, as measured by a metrics that you decide. And eventually, test the inference performance and determine if you have to do further improvements. This is a learning process that might require multiple iterations to get it right. A combination of these techniques help us on this prototype to increase the confidence of the model and improve the overall performance. You can even change your algorithm in case things are not going as expected. SageMaker allows you to bring your own model or algorithm And you could even use open source implementation, such as YOLO, which is a well-known object detection algorithm. While I spent time in the previous part of the presentation to talk about the core ML capabilities that are required to run an ML workload, that is not actually enough to run the system and scale it to more production line. ML systems indeed include additional software components that are usually hidden, but still required to make the solution work as expected. Configuration, data collection, feature extraction, monitoring, and many other parts are required for an ML system to run and operate in a production environment. With this, I wanted to introduce the next part of the presentation, where I will focus on how to automate the specific use case that I have described earlier in a way to provide a repeatable deployment process that could be extended to multiple production lines. The focus of our pipeline was to enable even business decision makers to create and deploy new models to solve the same use case for different production lines, by leveraging on a simple UI that will navigate that mean towards the various steps required in order to train and deploy a new model. To proceed with that, we will leverage on the learnings and implementation done during the first design phase, where we work on preparing data, architecting the solution, and implementing the core ML capabilities. During the previous phase, the core ML capabilities were implemented inside Jupyter notebooks, where most of the code and initial testing will reside. We will require an additional effort to identify what can be automated entirely, for example, by invoking SageMaker API to train and compile the model, or extract the data preparation part to be standalone. We will need to verify where is actually required some sort of user input, and eventually provide tools via dedicated UI, where also who is not necessarily familiar with implementation could actually go and create new model to be deployed in a specific production line. The UI will help to glue together the various steps and collect input in order to proceed towards the steps of the pipeline. We could start by picturing what process we are trying to implement. This helps to identify the pipeline visually and create a process flow which we will need to follow that contains all the steps that we have identified earlier, plus additional one required to complete the deployment. In each of the steps, there will be action performed via API, AWS Lambdas, or AWS step functions. In any machine learning workload, the data acquisition part is crucial to build a reliable and efficient model that will be able to run the inference with the expected performance. This phase could be implemented for both new model or existing model. In case of existing models, the data will be added to the initial dataset, which could help to improve existing model performance. For brand new models, which were never trained before, the dataset will serve as a ground truth to train the initial version of the model. For the specific use case, data is collected from edge device and saved in an Amazon S3 bucket, where it's stored and utilized in the next phase of the pipeline. When the data acquisition phase is completed, we can start to do the labeling job. The admin will configure the labeling job by providing information about the task to accomplish and define the working force that will perform the labeling. Both bounding boxes and image classification labeling are similar in the architecture. They only differ by the input images and input parameters provided by the admin. This is one of the phases of the pipeline where user input is required. The question is, how would we know when the user has performed the labeling and the job is completed? One way to solve this problem is by leveraging on Amazon S3 event notification to trigger an AWS Lambda function that will move the pipeline to the next step once Amazon SageMaker ground truth writes the output annotation in the configured Amazon S3 bucket. This will automate the process and guarantee the pipeline to proceed automatically. In a real scenario, you must still want to ask the admin confirmation to actually proceed to the training phase, but potentially, if this is not required, can be totally automated. The training phase is the most important in the pipeline, and it has been implemented by leveraging on AWS step functions that provides an ideal solution for implementing long-running workflows that could take hours or days to be executed. With AWS step functions, we can integrate multiple AWS services directly or utilize AWS Lambda for any custom implementation. In the specifics of this prototype, we used AWS Lambda to pre-process data coming from the labeling phase. In some cases, we extended the dataset by providing data augmentation features, while in other instances, we split the images into training and validation dataset. After the pre-processing is completed, we will start the training phase and eventually compile and optimize the model for the target edge device using Amazon SageMaker Neo. Model metadata and other information are saved inside Amazon DynamoDB and accessed through an API layer by the UI to provide information to the end user, while model artifacts resulting from training and compilation are saved into Amazon S3 and used in the subsequent step. After the training phase has been completed, we would have all the necessary information to actually deploy the models at the edge. The models are located in an Amazon S3 bucket and used by other services to perform the deployment. As the nature of this prototype required edge deployment, we have implemented that by using AWS IoT Greengrass. For other use cases, this phase could be implemented by invoking Amazon SageMaker APIs to create endpoint to be used for the inference. Along with the models, we deploy additional Lambda functions that run at the edge, which have the logic to extract frame, perform the inference, and send the data to the cloud, where it will be further analyzed for model improvements or operational needs, such as notifying a supervisor in case the defect rate is higher than expected. All of this is provided with a management UI that helps the admin to perform deployment of the models in different production lines, create new one, or optimize existing one. The UI matches the process flow that I have just explained, but also adds a setup phase where the admin selects the device to target for the deployment and other information that are required in order to start with the data acquisition. Most of the steps in this pipeline are automated, even though the admin is asked to perform a confirmation before proceeding to the next steps. Based on your use case, this could be further improved by skipping confirmation and proceed automatically. Technology always makes progress, and I would say the progress is faster than we would expect. It's always suggested to keep improving and reevaluating solutions that have been implemented in order to reduce legacy and tech debt. The prototype I went through today was built during 2020. Since then, AWS has released a large number of new features in the AWS ML stack, some of which would have been really helpful if we had them when we were working on this project. You can see some of the new features launched at AWS reInvent 2020. In the next slides, I'll be talking about the one that will have helped us on this project. Amazon SageMaker Pipelines is one of the new services that will be suitable for this use case. SageMaker Pipelines takes care of all the heavy lifting involved with managing the dependencies between each step of the workflow and orchestrate them so you can scale to thousands of models in production and expand your use of machine learning across more lines of business. SageMaker Pipelines provides comprehensive steps, including data preparation, transformation in data wrangler, algorithm setup, debugging, model optimization, and many more. Pretty much anything you can do in SageMaker, you can add to your workflow. To help you to start quickly, SageMaker Pipelines offer pre-configured templates for model building and model deployment pipelines, and the templates are fully customizable. Another new service that will have been very helpful for this project is Amazon SageMaker Edge Manager. As this prototype, more and more applications such as industrial robots, autonomous vehicles, and automated checkout require models that run on edge devices. ML models on edge devices is challenging because, unlike services in the cloud, devices have limited compute, memory, and connectivity. With Amazon SageMaker Edge Manager, you can automatically prepare ML models with high performance and efficiency across a wide range of CPU, GPU, and embedded devices. You can easily deploy model using any mechanism you choose, including AWS IoT Greengrass. Compared to hand-tuning models, customers using SageMaker Edge Manager save up to 6 months of development time, and see model performance improvement of up to 25 times. Additionally, SageMaker Edge Manager continuously monitors each model instance across your device fleet using Amazon SageMaker Model Monitor to detect when model quality declines. Last but not least, Amazon Lookout for Vision would have been helpful for identifying defects in the images. With Amazon Lookout for Vision, manufacturing companies can increase quality and reduce operational cost by quickly identifying differences in images of objects at scale. For example, Amazon Lookout for Vision can be used to identify missing components in products, damage to vehicles or structures, irregularities in production lines, small defect in silicon wafer, and any other similar use case. Amazon Lookout for Vision is fully managed and comes with pre-trained anomaly detection techniques for defect detection tasks, so that you don't have to invest your time and resources on creating a deep learning pipeline. You can begin using Amazon Lookout for Vision to automate inspection of images and objects with no machine learning expertise required. We have reached the end of this session, and I'd like to share some additional resources that you'll find helpful when starting your MLOps journey. You can learn and use this as example to build your own pipeline and operationalize your ML model effectively. I hope you have found this session useful. You joined the AWS Summit to learn, and you can keep the learning going after the summit with resources from AWS training and certification. We offer over 65 courses, many available for free and on demand, as well as virtual instructor-led training. AWS Expert will help you or your team to learn to apply ML to your business, unlocking new insights and value. When you are ready, prepare for the AWS Certified Machine Learning Specialty Exam, which validates your skill and provides an industry-recognized credential. For more information, visit aws.training/machine learning, and be sure to check out our AWS Ramp-Up Guide to learn more. I want to thank you again for attending our AWS Summit, and please don't forget to fill in those surveys. Have a great day.